I hope it doesn't fail again. All right, let's try this again. All right, so that diagram is really the basic, the start of this whole thing. Okay, so we've got, as I said, Bob and Alice. Okay, and we have a communication. And I'm saying that we're going to use SSL TLS to do this. Right, but this involves quite a bit, right? So there's quite a bit of things that need to happen. This is basically a laptop or the client. And this is a server, right? Amazon, the bank, etc. Okay, so, and this is, a web server basically as well. Web. Okay, so those two goals are really what drives us to build this whole thing, at least, right? So we want to have no eavesdropping, confidentiality. And then we have integrity. And then we have other things that we want to achieve, but those are the two main goals. So SSL has a meaning, stands for the secure socket layer. Okay. SSL stands for secure socket layer. And it's not very helpful to provide a definition of this. Instead, what's important is to try to understand what are the things that are happening with this protocol, and then how do we actually achieve them. So you can call it for now just a SSL as a protocol of secure web traffic, but there are two main parts. So it's got two main parts. Okay, two main parts, which are really to transmit the data. Now, you guys did this last week, right? You had the problem actually of sending the data to your friend via email. So that's transmitting the data, and you know how to do it, right? But what was the problem that you encountered to do that securely?
We had to send the key with it.
You had to send the key with it, exactly. So that's the second objective of this. Is sometimes this is called the handshake protocol, but basically to establish a shared secret key. All right, so that would be, so let's say 1 and 2. Okay, so these are the two main parts, and this one would be establish a shared secret key. Secret. Sounds simple, but a lot goes into this. And if it wasn't for basically a whole set of math and then a set of algorithms, this would not be possible in a practical way. Okay, so how do we solve this one? So some of you probably already know this. How do we share the secret key? For now, this is a complicated topic to grasp. We'll spend like 3 weeks or so on it, but basically there's something called a PKI infrastructure, which stands for public key infrastructure. All right, so there's a system called public key, and that's what will allow us to establish a shared secret key. Okay, shared just means that both parties have that same key. The key itself is secret. So how do we, once we've established a shared secret key, then it's easy. That's actually pretty easy, right? Once you do that, then you start to transmit the data with that secret key. Does that make sense, guys? And this is kind of the thing that you were doing before. Okay, so then this implies that we have on one side Alice, and on the other side we have Bob. And they both have the key, which will be denoted in this class usually by K. All right, and that just indicates that is the same key for both parties. Okay. So now let's establish what is called. So this is what, once you have a shared secret key, that's usually called symmetric encryption. Okay. So be aware of that because there's going to be a lot of terminologies. There's going to be like DES, AES, etc. You've used AES. Those are implementations of a framework. So the way that this works is usually somebody first has an idea or a goal, then they kind of work out what they want to achieve. They provide the formulation, which is going to be probably a mathematical formulation. They start doing a whole bunch of proofs, right? And then the implementations begin. The implementations are not necessarily the mathematical framework, right? And then you do one implementation, and then you do another one, and another one, and another one to make them more complex. When we start looking at the algorithms, you will see how they can be different, okay? But in general, without us having to worry about the specifics of an algorithm, we can define symmetric key in the following way. So the term is symmetric key. So that's where we start, right? When you start talking about cryptography, this is the first topic, basically, symmetric key encryption or symmetric encryption, basically. So symmetric encryption. And this will be denoted now by several things, which is what I will provide. So once again, we go to Alice, but we're just going to define this a little bit more formally now. So Alice and Bob who want to communicate, right? So we have here, right? And then there's, let's say a communication channel in that direction. This is an insecure channel. What do you have as an input from Alice is going to be M, which is the message. This will denote the plain text message. Okay, so M. This is going to be your encryption algorithm, E, right? Some way of converting from a message from plain text to ciphertext. Because it's symmetric encryption, you assume that you have also a shared established secret key, right? And that's K. And then here you're going to have the relationship of all of these, which is going to be E, the encryption algorithm, which takes as input K, comma, M, all right? And that is equal to C, all right? So where we don't actually have to worry about the specifics of how we do the encryption yet, because as you've seen, you can have AES, DES, and then several modes of operation as well, okay? On the other hand, what would you expect to have? If on this side we have an encryption algorithm, then on this side we would have what? A decryption. Very good. Decryption algorithm, D. All right. And this also takes as input the same key, right? That's the key thing. Now I'm going to say some additional things about these parameters, but in general, this is how it works. So on this side, we're going to have the decryption algorithm, which will take the K, comma, C, which is the cipher, remember, and this will be equal to M, which is the plain text message. And this is the relationship of symmetric key encryption. And as we will see very shortly, I will give you the exact math operation, which makes sense because that's how computers work, right? Of how to do the encryption, basically. All right, so let's provide a few other parameters that are pretty important here. K is the secret key. All right, so I'll move to the next notes. So K, I'm going to list out some important things. So K is the secret key. Usually, when you talk about keys, you assume that they are basically bits. So a stream of bits. That's good enough, right? Because any operation that you have, where you have text or you have numbers, boom, you can convert it to, the whatever you want, like the hex or the binary, right? And perform the operation at that level pretty efficiently. Okay, so you can say something like, well, it's probably around 128 bits. And you quantify, usually, there's a chart in the slides that I provided that you can take a look at, where you can see, well, the larger the key is, this is how much longer it would take to break the encryption algorithm. All right. And sometimes that's it. You know, sometimes the algorithm can be broken, but it would just take what? A month to break it. By that time, if you're making a transaction with Amazon, you're done. You're done in seconds, right? Or minutes, or 10 minutes at most. And if you leave it open, Amazon will just like, you know, kill the connection. So it will never be used for a month. So even if they broke it, there's no point. Now, this one is usually, I've noticed students are always surprised by this one, but it's true. The encryption algorithm is publicly known. It's not a secret. How it works, it's not like you have to keep it like in a lockbox and nobody should know what the encryption algorithm is. Actually, you want the opposite of that. You want to have what they usually do in cryptography, which is to have a conference every year and a competition, and everybody's trying to break these algorithms. And the security comes from the fact that they never break them, even though they know them, as long as they don't know the key, for instance, right? So everything is based on that. So we're going to say just very clearly, the encryption algorithm is known, is publicly known. So there's nothing there that's secret. The encryption algorithm is known. No. All right. This is really important. So RSA, DES, AES, all these encryption algorithms are known. Okay. They're not a secret. And you guys, so another thing that happens a lot is students are like, oh, there's this one called Blowfish, and there's this other one, star something or whatever. All of those are just implementations of these ideas. It's not like there's 100 ideas. Okay, guys? SSL is pretty much like the general idea, and then there may be variants of it, you know, in this direction or that. And if you find one, now elliptic curves, for instance, that's a different approach. But even that has some components of SSL. Okay, you use the parts that are good and then try to improve it in other parts. But in general, that's the interesting thing about cryptography, is that you may have 200 implementations with different funky names, but they're all based on the same ideas and the same primitives. Okay, very important. All right. So E, which is the encryption algorithm or the encryption version, is the encryption algorithm, and D is the decryption. So I'm just gonna encrypt, decrypt. Okay. So that's the encryption and decryption algorithms. The only secret in symmetric key, so currently I'm only talking about symmetric key encryption. The only secret is the key. That's it. That's the only thing you need to definitely protect. If you give that away, then you're in trouble. All right. So the only secret is K. Okay, the C, as we defined it before, which is the key, the secret key of some size, like I said, 128 bits, etc. All right, so now what is the operation for encrypting things, right? So let's think about that. So this is a fun thing because it's actually super easy, right? So what do we need to do? We need, we have a message, we have a key, and we want a cipher, correct? Now you can imagine that this message is, some sentence, Klein Mount Nitaka, right? So that's a classic statement. You guys know where that's from? That's what the Japanese used to attack Pearl Harbor. It was the secret code, Klein Mount Nitaka. So, so that, that in the past, they used that, that was the message that maybe they wanted to encrypt, who knows, right? So then you have some string of data, and then, or message, for instance, like that one, and then you have a key, and then you want to encrypt it so that people don't know what's being said there, right? Now, as you know from the ASCII table, which I provided, by the way, in the folder, You see it there. You can go from letters to numbers, right? So you can go from letters to hexadecimal, and then you can go to binary and so on. So we're just going to assume that we've already converted our messages into binary. Do you guys see that? So when I say binary, you know, so a byte, right? So what is a byte? How many? 8 bits. There you go. So it's a sequence of bits, right? And you know how you can represent different things with that, right? So, you know, the combinations. So you've done that before. All right. So let's think then that we have 1 0 1 1 1 1 0 1. That's my message. Okay. Convert it from the string into the sequence of bits. Now the key then should also be the same thing, because at the end of the day, everything in a computer is what? Everybody says computers are digital. Everything in a computer is zeros and ones, right? So it doesn't matter. So then let's say the key is this one, 0 0 1 1 0 0 1 0. Do you guys see that? And then what if I now give you the following pop quiz? Not a quiz, it's an exercise. It's an exercise, right? So all of these, I do this a lot, but they're exercises, not quizzes per se. So let's say that I give you this. The cipher is 1 0 0 0 1 1 1 1. So Bob and Alice again, you're going to send a secret, the message, right? And then you should send this one, right? So how does it work? So we got Bob over here, and we've got Alice again. So Bob takes M, right? This one. That's, you know, as we saw before, the message. I'll do the little squares. And Bob takes the key, which is this one over here, right? And then produces the cipher. And then Alice has the key and gets back the message. Yeah. What operation? So then we have an encryption and decryption algorithm, which I said there's an encryption and a decryption algorithm. But the encryption and decryption algorithm could be very simple. So in this case, who can tell me what the algorithm is? Oh, yeah, go ahead, please. It is XOR. Very good. It is XOR. That's it. So XOR is the operation. XOR, you know, it's you. I'm sure you've done the truth tables and all of that, and you looked at these, and that's actually, believe it or not, that's the operation. Now, should you only use XOR? Well, actually, Claude Shannon says that under certain circumstances, yes, that's enough. However, we can't really use that simple approach. So that's where the algorithms come in. So you can imagine you have XOR as certain steps, but there's more to it that you need to do to add complexity and be able to process things. But we're going to talk about that. Got it? So I'll prove this in a second, but this is the idea. So we concluded that XOR is that. So usually what you can do is either on this side or that side, you can just write something like that. And then that completes basically the operation and you know what you're doing. Okay. And if, you know, now I'm just going to do an example of XOR just to kind of remind you. Oh, sorry. Okay. So let's kind of go back to XOR. That's XOR. So this is just a truth table. If you want it in words, it would be one or the other, but not both. That's kind of how you would say that. And then the truth table you probably learn at some point. And so just now we don't have to do all the other operations. It's just XOR all semester. So just kind of memorize it and you'll be good to go. Okay, so I may give you on the exam a few, like I might give you like, you know, obviously the message, the key, and ask you for the cipher, you know, in some way. So here we have 0, 0, 0, 1. At some point, we're also going to do this in Python just to kind of prove that we can actually do the operation in code. But for now, so just by hand, okay, so 0, 0 would give you what? If you XOR those two. 0, yes. What about 0, 1? 1. What about 1, 0? 1. And then 1, 1, 0. And that's basically it. That's XOR, that's the truth table, and that's what you need to do. So now you can prove to yourself that you can do this. Got it? Make sense? Any questions on this one? Pretty easy. All right. But at some point, we will do like a simple code example where we will need to encrypt things with XOR, and we'll implement that in Python. All right, so let's keep going. All right, so as we said, the core of cryptography then is the secret key establishment, okay, and then the secure communication with that established secret. So let's now provide a more formal definition, I guess I would say, of symmetric ciphers. Symmetric ciphers. Okay. So a definition here for this would be a cipher is defined formally as a pair of efficient algorithms E comma D. Okay, so we're going to say a cipher. A cipher is defined as a pair of efficient algorithms. And actually, this keyword efficient is very important because you can have a really great algorithm that takes forever to encrypt things, and then that's not useful, right? If it takes you 30 minutes to download that movie from Netflix, you're probably going to give up and switch to some other service, right? So it has to also be fast. And so performance is actually one of the things that we will look at in labs, where we will see why actually SSL is the way it is, okay, for certain reasons. So it's got to be a set of efficient algorithms. Okay, and that's E comma D. Okay, where we can say E K comma M gives you C, and D K comma cipher gives you M. Given the consistency equation, which should look something like this: D parentheses K comma E of K comma M equals what? How do you complete this consistency equation? Okay. Equals M. Very good. Exactly. That's it. It should work. There's the, you know, if it meets that, you're good, right? Obviously, if it doesn't, you're not going to be encrypting. Got it? All right, very good. So yeah, so that's kind of the formal definition, and a lot of cryptography is kind of like this. It's very simple things, but you state it in certain terms. Okay, so given the consistency equation, so I'm going to say, yeah, K E K M equal. Very good. Any questions, guys, so far? Nope. All right, so today we'll probably start talking about Claude Shannon, who's really important, right? You guys should know who he is. Okay. So E is often, so D is always very deterministic. E can be randomized. And that's, so for instance, the initialization vector that we had before, we provide, you can see how now that you know that you XOR, the trick is to XOR sequences of bits, right? So now if you make everything, you establish a block size, then you just, you have blocks of, let's say, 16 bits. And then now you're just XORing, so you can add more things to XOR. And one nice way to randomize the process is to have an additional block, right? Like the initialization vector, which simply allows you to add more randomness to your data. All right, so let's just, this is just like a comment. So let's say, for instance, E, the encryption algorithm, right, is often randomized. So it's often randomized. Okay, so but what you do here is you generate random bits to perform the encryption. So, well, how does that work? So we had C, M, and the key, right? So actually, let's not. Okay, so wait, let me give more space to this. What do I mean by this? So I have M, the message, right? Something like that. Then I have the key, and the key could be something like that. What do? The operation is XOR. And that, by definition, we've said that it gives you C, but we could say that it gives us a temp C, right? A temp C, right? Which is going to be something here. What would it be? We just did this, right? So, well, all ones, and then 2 zeros at the end. Oh, you backwards?
I don't know if I'm.
Well, I'm just gonna, I can do it. I mean, so we said that if it's zeros or ones, then that's a zero. So what do we have here that meets that condition? This one, right? So this should be a zero. This one also is a zero. This one's a zero. These, did I make more so this one and this one. This is a 1 and a 1, right? 1, 1, 1. Is that correct? Yeah. You can double, check my what I'm doing here. That's kind of what this produces, but let's just say that that's not the final cipher, because we want to add some randomness. And what that means is, well, we can use the initialization vector, for instance, just to add more, right? Another, the key thing is to try to generate something that's an initialization vector that is randomized values. Something like that. Do you see that, guys? And that's what that means. So obviously, when you XOR these two, then you get the cipher. So what that means is you've got a little bit more randomized data. Any questions? Does this make sense? Yeah. All right. So E is usually randomized, and then D is not, because you just need the initialization vector to kind of work your way back, okay? And that's basically the idea. So I've given you the operation, and then now let's go back in time to around 1917, right? So 1917, I think it's 1917, I want to say, somewhere about that. So, and we're going to go back to Bell Labs. and to a person named Claude Shannon. So do you guys know who Claude Shannon is? Nope. He's just like the father of the digital age, right? So this whole world that we live in, right? So he wrote a thesis of the logic, like the truth tables and everything as applied to computers. Invented something called information theory. So when you guys take your networking classes and you talk about the rate and of sending bits over a channel and all that, that's Claude Shannon also. He did that at Bell Labs, and then he got bored, and then he invented cryptography, right? So he did a lot of things, right? So before him, it was all about, like, computers were very much like the classical thing. If you ever thought about what the Nazis used in the Second World War, that's not like this. That's not modern cryptography. It's more like substitution kinds of things, right? And then he started looking at cryptography, and in particular, he wanted to answer just one question, and that is, what is a secure cipher? That's literally it. I mean, it seems like a simple thing, right? But how do you define that your cipher is secure? You guys see that? So that's basically what he was looking at. So let's talk about that. So the question is, what is a secure cipher? What is a secure cipher? Remember, we've already defined cipher, right? It's a set of algorithms that do the encryption from plain text to cipher and then back. So, that's the idea. So he looked at one particular thing called the OTP, which is an algorithm, if you will, of encryption, right? And it stands for the one-time pad. So this is really what he was looking at. And so I'll define this algorithm, and then he was just trying to answer the question, what makes it secure, basically. Okay. Let's go over here. So what is the definition of the one-time pad? Basically, we obtain a cipher through encrypting K and M. So where the operation is basically XOR. Okay, so XOR as we've defined it. Now, there's just one simple addition to this algorithm, and that is the following. K, which is the key, right? K is a random, needs to be, and this is important, a random. So that means you need to get a random value. Is it easy to get a random value? It's not so easy, right? Can computers give you random values? Why not? What do they give you then? There's random functions in computers. But pseudo-random numbers. Very good. Very good. Computers cannot actually give you random because they're using an algorithm. There's some predictability there. People add things like the time of day, something about the CPU to kind of add more randomness. But at the end of the day, it is an algorithm. Getting true randomness is difficult. Okay, you get it from maybe the world that we live in, right? Nature. But it's difficult to find randomness. So, but he's saying if it's really random, like a perfectly random sequence, right? Then you have random sequence of, so the key has to be a random sequence, of bits. And here's the problem. As long as the message. Okay, that's the one-time pad. So it's an XOR operation, but you only perform it once. And the key needs to be as long as the message. Okay. So is it feasible to do something like that? Let's say you want to go to Netflix and download 3 hour, Endgame, which is like 3 hours or something. You would have to then have a key as long as all of Endgame, the movie. You see that? Because the movie you can translate into a sequence of bits, right? Zeros and ones. At the end of the day, that's what computers are. But then you would need to have a key as long as the movie itself. Where would you get that key from? You see how it's not practical to do that. It's like you're downloading the movie twice. Think about that. So if it took you 10 minutes, well, a minute to download the movie, it's 2 minutes now. Do you see that? Imagine the entire world doing this. It's double the networking in terms of encrypted things. That adds up, right? And so it's not feasible to do that. And this is why we have some, block ciphers. What do we do with block ciphers? We cut the thing into blocks, right, of a specific size, and then we encrypt the blocks. And what that effectively gives us is that it gives us smaller keys, not keys as big as the message. But then what does that imply? Does that imply that our encryption algorithms are not secure? Right? Do you see that? So he's kind of stating you can achieve perfect secrecy, but your key needs to be a random sequence of bits as long as the message. And that's like, you've done it. Good job. But it doesn't work in practice. So you have to cut it in blocks. And so again, that's what I was saying. You now have a disadvantage, right? Because you've created this pattern that's happening. And you saw this pattern last week, right? Because we did something like this with the color image. Okay, so we'll get to that. All right, so here, and this is then why the algorithms get a little bit more complex. So we obviously, once we break things into blocks, we don't just XOR, we start adding complexity, making keys bigger, etc., just so that the algorithms are more secure, yet they don't have perfect secrecy. Okay, any questions about that, guys? Does that make sense? All right, so that's kind of where it's coming from. So it's coming from Claude Shannon. Okay. All right, so we're going to kind of, conclude with that part. Let me just plug in my.
Do you want me to pass on?
Oh yes, please. The course participation, I think we still have to do that this week and next week. So yeah, please sign in, guys. All right, so let's keep going. So the question is, is the OTP or the one-time pad secure? And that takes us to the profound question of what is a good cipher? What makes a cipher secure, right? Which is what I had said. So the basic idea then, so Claude Shannon really had to think about this one. And the only way that he could answer this question is through probabilities. So he created like this probabilistic answer, basically, that you can somehow quantify that by looking at, calculating probabilities. So the basic idea is, the cipher text should reveal no information, no information about the plain text. About the plain text. Okay, so think about this definition. The cipher text should reveal no information about the plain text. That's actually the basic idea of Claude Shannon's formulation of what makes a secure cipher. We saw this last week. We had two examples. One, we could see the triangle and the circle, therefore that cipher was bad. It didn't do the job. The other one, we couldn't, at least as humans, we couldn't figure out what the message was from the cipher, okay? And so that's really the basic idea of how you define a secure cipher. And he came up with the following thing. So I'll just write it out. So basically, this is the definition of what makes a secure cipher. The PR stands for probability. So really the goal with this kind of problem is you would have to calculate the probabilities, right? So look at all these messages over time. And then with this algorithm, how many times were you able to figure out the plain text from the cipher? Do you see that? So like if we repeated the experiment, well, we did two things, right? Last week, but imagine you did 10 of those for each one, then you would count how many times you were able to predict the plain text from the cipher, and then you can start to quantify it, okay? So basically here, the probability, so I'll write it out, and then you guys tell me what you think it means. So remember, PR stands for probability. That's it. What do you think this means? How would you interpret that? So you're comparing, don't try, like, for those of you that really love like algebra and stuff, don't try to move the letters. This is not algebra. This is like a comparison of one probability to another probability. So we're comparing this one to this one, and it's saying that they should be equal. That's really important. What do you think it means? Why?
Well, like the,
Yeah, so yeah, if that's your question, M0 means message 0 and M1 means message 1. You wanna, seems like you wanna attempt.
The probability that any one message encoded should be the same as like the probability of the other message being encoded.
Mm-hmm.
Visually, they should be similar.
Yeah, you're on the right track. That's what it means. You guys want to elaborate a little bit? So it's basically, what is the thing that Zelda will say? If there's Bob and Alice, we're gonna say Zelda is whoever is trying to like intercept, right? So if Zelda captures C, what, she doesn't have the key. Oh, thank you. She wants to, she wants to get the message, obviously, right? Maybe she's got a whole bunch of messages and she just wants to link that C to one of the messages to break things. Yes, please.
If she applies the key to either of those messages,
She cannot apply the key. She does not have it. Yeah, think about it, right? So that's the whole thing. You only have the C. Yeah. Yes. What message 0 or message 1, right? Yes, exactly right. Basically, if you have C, the C cipher cannot tell you that one is more probable than the other. You see what I'm saying? That's it. So you need to quantify that probabilistically, and then you say your algorithm. We can do that with the previous example that we did in the last class, right? With one, I could tell what it was. So, because I could intercept one cipher and the other one, right? I had both. You should have in your lab report the one where you see the square and triangle and the one where you don't see. So your conclusion is with the one where you can see the square and triangle, you can basically from that cipher say what the message was. It's a triangle and a circle. Got it? I'll write this down, but this is the interpretation of it. I'll write it on more like eloquent. But that's the idea of it. Anything, guys? Any questions? But yeah, good job. All right, yeah. So the parameters, you know already what they are, right? So encryption, decryption, the key. There's only one key because that's all you know so far. We've only touched on symmetric key encryption, right? C, remember we're looking at this from the point of view of CELDA. So whenever I say CELDA, I mean whoever intercepts the message is trying to steal, break confidentiality, integrity, etc. And really what we want to get is the message itself. So we're going to state this. So that means, let's just write it out. So that means, and it's pretty much what what's your name? I'm sorry. Quentin. So it's pretty much like Quentin put it. So let's just say that means right, given the ciphertext, C, right? You cannot tell if the message is more likely to be M0 or M1. Any questions? So that, that's kind of pretty much what we have said. So if so the probability is the same. And that's why we have that equal sign there. You see, they have this equal. It's not, this would be bad, right? Or this would be bad. Because one is more likely than the other. That's what cryptanalytics is trying to do. When you hear about like, and the NSA, or organizations that are trying to break codes, right? This is what they're trying to do. They're trying to, what is it more likely to be, and then go in that direction and further study it. Okay. All right. So let's go back. All right. So we've stated this. We can say the probability is the same. So if you're an attacker and you intercept a particular ciphertext C, then in reality, the probability that the decryption of C is M0 is exactly the same as the probability that the decryption will give you M1. Just what you said. So if all you have is the ciphertext, then you have no idea whether the ciphertext came from M0 or M1. And that's, the same thing that I wrote over there. But unfortunately, so we said that the one-time pad is secure, but unfortunately, this idea that it requires to be, so it's like two problems, actually. One is that you need to have, it has to be random, like really random, right? That's difficult. How do people get truly random data today? Do you guys know? Have you heard of any?
Is there like a lab in Europe that's got like a wall of lava lamps or something?
And how does that give you randomness?
Like fluid physics.
The fluid physics? That sounds right, actually. they're quantum physics, not even quantum computing, but quantum physics looks at particles. And then, although you don't know what the particles mean, at least you can measure all the particles. And because they're supposed to be really random, then you get a sequence of random values. So I think people have tried to make businesses out of creating like a box where you have particles that just like appear in one state or the other, and the sequence of that in theory is very random. Do you know what I mean? So that's like the extreme to achieve randomness. But yeah, your examples are pretty good. Yeah, go ahead.
I know Linux uses mouse clicks and like keyboard clicks together.
And why is it doing that? Because humans are possibly random, although would you say if you're left-handed and you're a student and you're kind of tired that day, that you'll have a specific pattern that someone else may not have? A little bit, right? So, yeah, you couldn't say, but there's a possibility that not every day you're doing different things. So eventually there's like a particular behavior that you have. So it's a difficult problem actually to achieve total randomness, but it's but the definition, if you do have the random, but also I should say, the stuff that we have like pseudo-random numbers do work, and the solution is make it longer, right? The bigger it is, the more likely you are to make it harder to break because it's longer, a little bit more random. But they are coming from algorithms, and so that's the idea. Any questions? All right, so I think we defined the OTP. So we're gonna do an exercise. So this is like one segment that we finished this segment, like so we haven't had any issues with the internet, thankfully. So I'm gonna